Hello, my name is Kainton, and today we are going to continue from tutorial 4, still on flow network. I hope you've been following this tutorial, and I think this one is going to be one of also the simple ones, simple tutorials. And today we are going to look at definition of a cut, capacity of a cut, examples, minimum cut problem. Remember to subscribe. Just click on the subscribe button down below so that you get notified when I make new lessons. Our minimum flow problem came from tutorial 3. Minimum flow problem is simply a problem that says, let me just write it because minimum flow problem is actually not part of this course, so let me write it in red. Is just from the previous mean flow problem. It simply says find the parts with minimum flow. So that's just it. Remember, we say that the flow can not be more than capacity, but it can be close to the capacity. Oh, well, this is maximum flow, sorry, maximum. With maximum, so it should be close to the capacity, but not more than the capacity. So find a path to the maximum flow. So you keep adjusting the flows through each of the edges of the graph until you get the maximum flow. So let's now go to cuts. What is a cut? Of course, if you take a knife, you can cut through something. And the same thing applies. So you can just cut through the network or the graph, but this is in a different sense. Let's look at the definition. It says it's a division of the graph into two partitions, A and B, such that some nodes are in partition A and some nodes are in partition B, right? Now there must be a constraint. This constraint says that partition A and B, T has to be in partition B and S has to be in partition A. Remember what S and T is. S is the source and T is the what? Is the sink. Alright, so for instance, if you have something like this, let's just take an example. And you have S, you have T, you have A, you have B. So if we do, let's put the arrows. Alright, so let me take a different pen color. So if we do something like this, we've not succeeded in cutting because here we have S and T in the same part and we have A in the same place. So this is not a cut. Here we have S, T, B in A. Then we have this in another partition, so it doesn't work. So let me erase this and let me try again. So let me grab my pen. This time I'm gonna use same color. Let's cut it this way. Alright, at this point we have, let's say this side is A and this side is B. So here we have S is in A while T is in B. So that is a perfect cut, right? So a cut is simply a cut through the graph so that some nodes are in A in one partition and other nodes are in B in the second partition. Okay, so we say that the capacity of a cut is the sum of the capacities of the edges out of the cut. Edges going out of the cut means edges going from A to B. So in this case we have this edge and we have this edge. So if we have 5 here and we have 2 here, what will be the capacity? Capacity of the cut will be what? 5 plus 2 equal to 7. So in this typical example, the capacity of this court is 5 plus 2. Alright, let's take some further examples. In this case, let's take, for instance, we have this court. We have now, sometimes the court may not actually be lines that actually cut in a straight way. So we can say A. Okay, let's take a simple example first. Let's cut it this way. Okay. Now, what is the capacity? What is the capacity of this court? Can you try? Okay, try to do it. Leave a comment and tell me if you got the answer correctly. The capacity of this court will be 2, right? Plus, because this is going out of the court, and we have this is going out of the court, and we have 2 plus 2 equal to 4. We are not counting 3, because 3 is going inside the court. From outside is going inside, because we have this is A and this is B, right? Another thing I would like to let you know is that you can define the partitions as A is equal to enumeration of S and what? And A. B is the enumeration of B, D, C, and T. Okay? Let me just teach you one notation that you need to know. Capacity of a court is written as capacity of the courts, A, B. That is how it is written, right? And now it's giving us summation of all the capacities of edges going out of the court. So we can say E out of A. So it can be the other way around, because we are talking of edges going out of the partition that contains the sink, right? Good. Let's take another example. Let's take, in this case, let's partition this. Let me take my pen. Let's partition this into 2 partitions of A and B. Okay. In this case, let's say A contains the following. A contains S, E, and D, right? And B contains, we say A contains S, E, and D. So you can see that in this case is also a court, and B contains every other node. So we have A, B, C, F, right? F, yeah. So in this case, you can't really draw a line across this court. So that helps you understand that a court is not just when you draw a line through. You can have a court that's defined by a court line in this case. So can we calculate the capacity of this court? CAB equal to what? So we say what is going out from S. We have 20 and we have 12. 20 plus 12. What is going out from D? So this and this. We have plus 10 plus 9. And what is going out from E? Just one, which is this, plus 25. So if we sum it, we have 20 plus 12, 22, plus 10, 32, plus 9, 39, plus 25, that should be 64. 64. So this is the capacity of this court, right? So we can continue to play around and then to understand that this is exactly what COT is all about. Let me now finalize by telling you what a minimum COT problem is. It simply says find the COT minimum capacity. So that is the minimum COT problem. Now let me ask you, this COT we did, CAB, is it the minimum COT? For sure it's not the minimum COT. Let's say we want to be smart and we just cut it from here, and we have capacity here to be 12 plus 20, which is 22. Is it the minimum COT? Maybe yes. Let's see. Possibly, yeah. So, but it may not be easy as easy as this in every other problem. There is some other problems I would have loved us to look at, but I've not had enough time to continue with this. This will do in the tutorials because I'm going to stop here and allow you to play around. So the next class will be, we start looking into greedy algorithms. I'd like to thank you for viewing. Click on subscribe button to subscribe to the channel if you've not done so. Yeah. And then we continue with tutorial 5.